Hello and welcome to Dr. Anima Upadhyay's Chemistry, Technology and Chemistry Lab videos. In today's video, we will learn about the determination of viscosity and viscosity index using Redwood Viscometer. But before we start this video, I would like you to please subscribe to my channel and also to like and share this video. Whenever we are determining the viscosity of a given oil, we must know the definition of viscosity. So, the viscosity of a liquid is defined as the resistance offered by the different layers of the liquid to its own flow. This is a flow property of a given liquid and it is affected by the change in temperature. As the temperature rises, the viscosity, that is the thickness of the oil, decreases and vice versa. So we can say that viscosity is inversely proportional to temperature and is expressed in centipoise. Now the question comes to our mind, why the viscosity of a lubricant should be determined? The answer is simple. The viscosity of an oil should be determined before selecting it as a lubricant because the performance of the machinery depends upon the type of lubricant used. Especially the property viscosity is extremely important. It determines whether a lubricant can be used for lubrication or not. Because the viscosity of the lubricant should not change at the working temperatures of the machinery. If there is a rapid change in the thickness of the applied oil, then it may lead to wear and tear of the machine parts. An oil which is highly viscous or thick at room temperature may get thinner with the rise in temperature of the machinery while the machinery is working. And if such a lubricant starts flowing as a result of getting thin, then it cannot be used in the machinery working at that high temperature. So what do we conclude? We conclude that only those lubricants should be used for lubrication which shows little or no change in viscosity at working temperatures even after a prolonged use. And this property of a lubricant which states about the thickness of the lubricant is determined as viscosity index, abbreviated as VI. So what is viscosity index? It is defined as a ratio representing the maximum decrease to the minimum decrease in viscosity of oil per degree rise in temperature between 100 degree Fahrenheit and 210 degree Fahrenheit. Since it is a ratio, therefore it has no units. Higher the viscosity index of the oil, lower will be the rate of change in viscosity of the oil with temperature. And better will be the quality of the lubricating oil. Mathematically, viscosity index is expressed as shown here in the formula L minus U divided by L minus H multiplied by 100, where U is the viscosity of the sample under test. L is the viscosity at 100 degree Fahrenheit of Gulf oils, which has same viscosity at 210 degree Fahrenheit as the oil under test. And H is the viscosity at 100 degree Fahrenheit of Pennsylvanian oil, which has the same viscosity at 210 degree as that of the oil under test. So what do we understand by Pennsylvanian and Gulf oils? To understand that, we must know that oils with maximum decrease in the viscosity are given an arbitrary value of 0 viscosity index. And minimum change in the viscosity are assigned 100 as the viscosity index. So the Pennsylvania oils, which are designated as H in the formula, are considered good with a viscosity index of 100, and they are rich in paraffins. Whereas the L designated oils are Gulf oils, which are rich in alicyclic and naphthenic hydrocarbons and has a viscosity index of 0. That is, they has a maximum decrease in the viscosity. So, whenever we are determining the viscosity of a given test oil, we use different types of viscometer. Here we are using Redwood Viscometer. So, the construction of the Redwood Viscometer is described here very clearly with the help of this diagram. For this, we require a brass cup which is around 90 millimeter long and 46 millimeter wide, and the inner wall of the brass cup is lined with silver. There is a small opening at the bottom of this brass cup into which fits the small ball lined with silver attached to a spring, so that we can raise this ball and open this opening, which is fitted with an agate jet, and the orifice of this jet is around 1.82 millimeter in diameter, and the length of this agate jet is 10 millimeter. A collection flask is placed below the opening of this agate jet to collect the oil sample in the brass cup at different temperatures. So, a lid is provided on this brass cup through which a thermometer can be inserted to record the temperature of the oil. This brass cup is then kept in a water bath, and the water bath is also provided with a thermometer and a stirrer to make the temperature of the water uniform, and the temperature of the oil in turn is raised with the help of water bath, which is electrically heated. The entire apparatus rests on a tripod stand. There is an opening for the water to come out, the outlet for the water from the water bath, and the water level is maintained in the water bath. So let us see the construction in detail I have given for your better understanding. Here I have described that it consists of a standard cylindrical oil cup made of brass. I have already explained in the figure, which is lined inside with silver. Cup is 90 millimeters long, 46.5 millimeters broad, provided with a agate jet in the bottom. The diameter of the orifice, I have told you, it is around 1.62 millimeters, and the jet is around 10 millimeters in length. A silver plated brass ball attached with a wire fits into the concavity of the agate to prevent the leakage of the oil from the orifice. The cup is provided with a lid with an opening to insert a thermometer, and the brass cup is placed in an electric water bath. The water bath is also provided with a thermometer and a stirrer. There is an outlet at the bottom of the water bath to change the water. So this is the actual instrument shown here. The whole apparatus stands on a tripod stand provided with leveling screws. So now see the working, how the instrument works. So first thing, we should level the instrument Water should be filled in the water bath up to the mark. The brass ball in the brass cup is kept in position to seal the orifice so that there should not be leakage from the cup. The oil is taken in the brass cup. Temperature of the oil and water in the water bath is noted. The beaker provided to collect the oil from the brass cup is kept below the jet. Ball is then raised to allow the oil to drop in the beaker below through the jet. And the time taken for the oil to come down into the collection beaker is noted using a stopwatch in seconds. The oil from the beaker is then refilled in the brass cup. Temperature of the water bath is raised, and this raises the temperature of the oil, and the process is repeated at different temperatures as shown here at 35 degrees, 45 degrees, 55 and so on. The time taken and the temperature are recorded in the observation table as shown here, and the graph is plotted to determine the viscosity index of the oil. So we can plot either the viscosity versus temperature or log viscosity versus temperature, where viscosity is taken on the y-axis and temperature is taken on the x-axis. And you can see here with these readings we are getting a graph like this. So it is showing that the temperature is up to 55 degrees, the temperature is almost constant, and after that the oil becomes thin. Now let's see with the standard graph that plotting the viscosity on the y-axis and temperature on the x-axis. The slope you can see with the green line, the slope of the lubricant is not very high. It is almost stable across a wide range of temperature. Therefore, it has a very high viscosity index. Whereas the blue line shows a low viscosity index because the slope you can see, it is changing rapidly with the rise in temperature. So it must be a naphthenic or the Gulf oil, and the red one, which is not as high as the green line and not as low as the blue line. So it is a high viscosity index. It could be some mineral oil with a viscosity index of 100. So what do we conclude? That a lubricant with higher viscosity index is desirable because it provides a more stable lubricating film over a wide range of temperature. Here also you can see that the viscosity index is high in this range 35 to 55. So this oil under test can be used up to a temperature of 55 degrees where there is very little change in the viscosity, which can be calculated using the slope. By dropping a perpendicular and joining it with this line, we can calculate the slope. Now, we should also know that the Redwood viscometers comes in two sizes depending upon the diameter of the jet for the outflow of the efflux oil, and they are designated as Redwood Viscometer 1 and Redwood Viscometer 2. So what is the difference between Redwood Viscometer 1 and 2? It is the diameter of the orifice. For one, it is 1.62 millimeter and it takes around 2000 seconds or less for the oil to outflow from the jet. Whereas the Redwood Viscometer 2 has a larger orifice diameter for around 3.8 millimeters and the outflow of the oil from the jet is just 1/10th of the flow time of the Redwood Viscometer 1. Otherwise, the construction, working and principle for both the viscometers are same. But if we are provided with a test sample which is very viscous, highly viscous, it is better to use Redwood Viscometer 2 because it has a larger diameter. But if the viscosity of the given test sample is average, not too high, then we can use the Redwood Viscometer 1. There are many other viscometers also. The commonly used viscometers in the labs are Engler viscometer, Saybolt viscometer, Ostwald viscometer, other than Redwood viscometer. So the Engler, Saybolt viscometer and Engler viscometer, they have same principle and working same as the Redwood viscometers. But there is a slight difference in the construction of the viscometers compared to Redwood viscometer. The Ostwald viscometer is entirely different from these three viscometers. It is made up of glass and it is also called capillary viscometer. So here are the differences tabulated in this table where we can see that the oil which is taken in the brass cup is provided with thermometer in Redwood viscometer, Engler as well as Saybolt viscometer. The oil is taken in a cup made up of brass and this brass cup is provided with a thermometer and this instrument works electrically. So the oil is heated electrically using a water bath in all these three. But in the Ostwald viscometer, there is no brass cup. The viscometer itself is made up of glass and no thermometer is provided. It works manually. In the Redwood, Engler and Saybolt viscometer, the cup which is provided to take the oil sample is provided with a jet and this jet in the Redwood viscometer is provided with a ball to close the cavity of the brass cup. And this ball, which is lined with silver, can be lifted using a attached wire to open and close this cavity. This opening, the jet. In the Engler viscometer, the jet is closed by a valve rod that can be vertically lifted through the lid. In the Saybolt viscometer, it is provided with a cork stopper. So these are the important differences in the brass cup. In the Redwood viscometer, the jet is controlled by a small metallic ball. In the Engler, it is provided with a valve rod that can be vertically lifted, and in the Saybolt, it is provided with a cork stopper, which is provided with a chain or a rope. In the Ostwald viscometer, there is no separate cup. Here, there are two glass tubes. One is wide, other is narrow, and the two tubes are connected with the help of a U-tube. So there is no separate brass cup. In all the three viscometers, that is Redwood, Engler and Saybolt, a collection vessel is provided to collect the test sample kept below the jet of the brass cup. In the Redwood, it is collecting vessel is 50 ml cup, In the Engler viscometer, it is a 2-bulbed narrow flask, and in the Saybolt viscometer, the capacity of the collecting flask is 60 ml. Whereas in Ostwald viscometer, the two capillaries which are connected by a U-tube, one is narrow, the other is wide. The lubricating sample is taken in the wide limb and it is sucked into the narrow limb, which is also having a small bulb with a mark above the bulb and a mark below the bulb. The liquid is sucked with the help of a suction or with your mouth and above the mark above the bulb in the narrow tube, narrow limb. And the time is recorded when the liquid from the upper mark flows to the lower mark of the bulb. How much time it takes? Thermometer is not provided with this. So, Ostwald viscometer is little different in construction working from the rest of the 3 viscometers. I have explained the Ostwald viscometer in detail in one of my videos. If you want to learn the Ostwald viscometer, I will give you the link of this video in my description box. Hope you have understood determination of viscosity using Redwood Viscometer. If you have any queries, leave a question in the comment box. Thanks for watching this video. Please press the like button and share this video among your friends. Also subscribe to my channel.